In the northern sky, between Ursa Major and Leo, there is a faint constellation that most star charts barely acknowledge. It is called Leo Minor. Within it, roughly 2 billion light-years from Earth, sits an elliptical galaxy, catalogued as J1007+3540. In visible light, it is a pale, unremarkable smudge. But in 2007, radio astronomers at the University of Leiden turned a different kind of instrument toward this galaxy. They were not observing light. They were listening. They were detecting radio frequency emissions, oscillations far below visible wavelengths, invisible to the human eye, inaudible to the human ear. And what they found did not match any known radio galaxy template. 2 sets of jets. One ancient, stretching across nearly 1 million light-years of empty space. One new, punching outward fresh from the galactic core. And between the two, nothing. A gap of roughly 100 million years. A silence so long that when it began, complex multicellular life on Earth did not yet exist. The old jets were relics. Vast lobes of radio-emitting plasma, cooling and fading, pushed outward by an engine that had been active when the most advanced organism on this planet was a single cell. At the center of J1007+3454 sits a supermassive black hole, millions of times the mass of the Sun. For 100 million years, it consumed nothing of consequence. No accretion disk forming around it, no magnetic fields winding into organized outflow, no radiation escaping the core, just mass and gravity and silence. Then it fired again. New jets erupted from the galactic core, plowing directly into the ghostly remnants of the old ones, but this time, the surrounding environment fought back. The intergalactic medium, a diffuse, superheated gas that fills the voids between galaxy clusters, pressed inward on these new jets from every direction. Under this pressure, the jets did not extend in clean, symmetric lines. They widened, they bent, they deformed. Radio telescopes rendered the resulting shape as something resembling a volcanic eruption, wide at the base, narrowing toward the top, a plume rising through resistance. The discovery was made possible by LOFAR, the low-frequency array. It is not a single dish. It is a network of roughly 20,000 individual radio antennas spread across the Netherlands, Germany, Poland, France, Sweden, and the United Kingdom. Together, they function as one telescope, operating at frequencies between 10 and 240 MHz, far below what most radio observatories detect. At these low frequencies, old plasma becomes visible again. Emissions that had faded to nothing at higher frequencies reappear. Through LOFAR's data, the full biography of J1007+3540 emerged. Structures that were thought to have vanished lit up like old ink under ultraviolet light. The ancient lobes, the 100-million-year void, the restart, the deformation. Each chapter written in radio waves. The mechanism behind the restart remains uncertain. Supermassive black holes do not simply switch on. They require fuel, gas funneled inward through a disk that heats and compresses until it radiates across the electromagnetic spectrum. One hypothesis involves a galactic merger. Another galaxy, or a large cloud of gas, drifting close enough to feed the black hole fresh material. A second possibility is internal. Gas in the galaxy's own halo, cooling slowly over millions of years, may have finally condensed and fallen inward, crossing the threshold needed to reignite the jets. Whatever the cause, the physics of the deformation is better understood. Jets from active galactic nuclei typically extend as narrow, collimated beams, held together by magnetic fields tightly wound around the outflow. But when those jets meet resistance, dense gas, pressure gradients, thermal turbulence in the intergalactic medium, they lose their shape. They spread. In J1007+347, the ambient pressure was strong enough to reshape the jets entirely. The classic double-lobed butterfly of a radio galaxy gave way to something rounder, something that billows. The LOFAR observations were published in 2022 by a team led by astronomer Aleksandar Shulevski at the University of Leiden. The team measured the spectral age of the plasma, the time elapsed since electrons were last accelerated to relativistic speeds. The old lobes returned spectral ages exceeding 100 million years. The new jets, under a few million years. Between them, no intermediate population at all. A clean break. The black hole did not flicker or sputter, it stopped completely. And then it resumed. J1007+3440 is not the only restarted radio galaxy. The class is small but growing. 3C236, one of the largest radio galaxies known, displays similar dual epoch structure. Centaurus A, just 13 million light-years away, shows evidence of multiple outburst cycles spanning tens of millions of years. But J1007+3540 remains distinctive because of the deformation, a visible record of a jet fighting its environment and losing its form. This matters beyond classification. Most models of galaxy evolution treat black hole feedback as continuous, energy injected steadily into surrounding gas, preventing it from cooling and forming stars. J1007+3440 suggests this feedback is episodic. A black hole can heat its environment, go dormant for 100 million years, and resume with enough power to reshape intergalactic gas across 1 million light-years. 2 billion light-years from here, a supermassive black hole that had been silent since before the Cambrian explosion fired again. The jets it produced were bent and crushed by the thin gas between galaxies until they resembled something almost organic, a plume, a bloom, a volcanic column rising through a medium that refuses to move. It is still active now. The jets are still pushing outward. The intergalactic medium is still pushing back. No one observed the moment it restarted. By the time the light reached any antenna on Earth, the new jets had already been burning for millions of years. What we see is not the event, it is the aftermath. A black hole caught mid-sentence, with no record of what made it speak again.